Okay, perfect. So without further ado, I'll pass it on to Scott. I just want to say that he's the author of The Causal Inference, the mixtape, which he has made publicly available on his website, and that accompanies with a Spotify playlist. It's pretty awesome. I'm really happy that he's with us today to talk about new developments and differences. So I pass it on to you. Thank you again.
Thank you, Sevi. I can hang around after if anybody wants to talk. I just know that I really wanted to get to a simulation. I felt like if I showed you this simulation, which I can send to everybody, that it would appropriately give you anxiety similar to the presidential race in the United States has given you anxiety, or maybe has given you anxiety. So hopefully it'll sort of drive it home. So let me go ahead and start. Let me share my screen. And let me make this large. So this is recent developments in differences. And I'm only, this new development in differences is actually, really exploded in the last 2 years. Both work by applied people. There's been, I think, a lot of discoveries by predominantly applied social scientists about some, fairly nuanced but really critically important things, as well as it's gotten the attention of really excellent econometricians. So it's an exciting time, and you could probably spend several weeks just on this new material. But I'm going to just cover two things. I'm going to cover the problem with the two-way fixed effects estimator, which is really the workhorse estimator that all of us have used or is planning to use for estimating a particular kind of scenario with a diff and diff design. And then I'm going to talk about a new estimator by Callaway and Sant'Anna that I'm going to kind of offer to you as being a superior alternative to two-way fixed effects that suffers from none of those problems and really does do all the stuff that you already were hoping two-way fixed effects would do. And then hopefully I have time to do a simulation that kind of will compare these two estimators performing under different scenarios. So probably a lot of people know this already, but differences was actually developed by, like the very first epidemiologist in the 19th century during, interestingly enough, a massive pandemic like we have today for cholera. And at the time, the widespread belief was that cholera was spread through the air, not so differently from COVID, although they didn't really think even about water droplets. They just sort of thought it was transmissible kind of person to person in close proximity. And John Snow believed it was actually spread by water. He presented a lot of evidence. And he developed the 2x2, the simple 2x2 differences design that showed, the strongest evidence that it was actually waterborne. It didn't get entered into economics in the way that we kind of, have today until Orley Ashenfelter did so in the 1970s, studying a bunch of job trainings program. But I don't get the sense that really took off, although you do see it, you do see it in, for instance, Bob Lalonde's review of very common estimators in his famous 1986 American Economic Review paper. It really kind of took off with David Card and Alan Kruger in the 90s, particularly their study of the minimum wage. And it is now, if you count the number of times differences is used in the abstracts of papers at the National Bureau of Economic Research, it's the single most popular research design, even more popular than randomized control trials. So more than likely, you're gonna be using differences for your own work, or at least in reading in your own work from other people. It's the most common, so it's very common. So the most common situation, though, is very subtly different than the kind of thing that John Snow was looking at, or even what Alan Kruger and David Card were looking at, or even Orley Ashenfelter. The most common situation is where you usually have a group of panel units. It's oft almost, a lot of the time, it's like a region, or in the United States, a set of states or a set of cities that get a quote treatment, like some policy intervention at a different point in time. It'll be a different set of groups that will get treated at different points in time. And because ordinary least squares with fixed effects will handle a situation like that really trivially, and then allow you to add in a bunch of controls and sort of, calculate standard errors really easily. It's become really popular to estimate average treatment effects using the OLS estimator with fixed effects, or what's commonly called the two-way fixed effects, because it's two-way because it'll include, time, such as year or month, and panel unit fixed effects. So it's really if any of us goes back to econometrics, is what we learned in our panel class, like, early on. But new econometric work has shown that this model can be, and almost certainly is, in most of the studies that have been written, it's severely biased. And I'm not saying that we should make a cottage industry out of going back and redoing all those papers, but probably going forward, we need to be better. So what I'm going to do is I'm going to discuss the bias of the two-way fixed effects estimator. I'm going to present a new solution, and then I'm really hope that we have time to go through a simulation. Okay, so let's start with the simple 2x2 model. Now it's called 2x2 because there's only going to be two groups. There's going to be a treatment group that is treated at some point in time. We'll call that, the period between pre and post treatment. So it's like some sort of period. We sort of measure their mean level of some outcome in the pre-treatment period. We measure it in the post-treatment period for the treatment group, separately for the control group. And we just do a set of differences. We do a difference for the treatment group. We do a difference for the control group. Then we do the difference in differences. All right, so we're going to difference those two differences. We already knew that. With some simple algebra, we can take that very simple formula. Basically, all we do is we add in a 0. Notice we have this 0 here. Expectation y0 post minus expectation y0 post. So, you can add in that 0, but once you rearrange it, you can see that that 2x2 that we just talked about actually kind of is broken down in causal terms. And notice that once we start putting subscript or superscripts up here, notice that's different than what we had here, because these are potential outcomes as opposed to the outcomes that will be in the actual data. We'll get expectation y1 in the post period. That is an observed set of data, because that's post period for the potential outcome, which means in a world where it's treated, what is its expectation for that treated period, minus expectation y0k for the post period. And this is a counterfactual, because we do not observe y0 in the post-treatment period, because we said that the K group is being treated, and therefore we only observe y1 in the post-treatment period. But nevertheless, that's the parameter of interest. And that's how usually these, that's how this notation almost always goes, is it's expressed in terms of potential outcomes so that we can get into some causal parameter. And then we add in there was a plus sign here, so we're going to add that in, and we can see here that delta hat, the thing that you calculate with the data using this difference and differences here, only equals the causal parameter of interest in the 2x2 if this term right here zeroes out. Okay, and that's the parallel trends assumption that every diff and diff paper basically kind of waves its hand on and says, I'm going to assume parallel trends. But the problem is, this simple difference here actually only applies to this scenario, to the simple 2x2. It does not apply to the more common scenario where groups get treated at different points in time. When you are using the two-way fixed effects estimator, it is not enough to assume parallel trends. So parallel trends is not enough for the papers that you've been working on and the papers that you've been reading. In order for two-way fixed effects to be an unbiased estimate of some average treatment effect, you need more assumptions with differential timing. And this was discovered by a couple of papers, but I'm going to talk about Andrew Goodman-Bacon's paper in his 2018 and 2019 working papers that you can download from his website. It uses the Frisch-Waugh theorem to decompose that difference, that two-way fixed effects estimator, into what it really is. And if you see what it really is using that decomposition, then you can see where all of the biases originate. And then you can see that if you can't credibly appeal to the assumptions needed to get rid of those biases, two-way fixed effects is biased. And this is really kind of interesting, and I don't have a good answer for this, but this is all driven by heterogeneity. That's the cause of this. It's the heterogeneity within that treatment effect. And when we were learning our fixed effects estimator in our panel classes, we were implicitly assuming constant treatment effects. It's just not often stated because traditionally we are teaching those estimators without using the potential outcomes notation. And it's really in the potential outcomes notation that heterogeneity really kind of it gets in your face, okay? And the problem is, it's not just the heterogeneity that's the problem. The problem is two-way fixed effects with differential timing. The reason it's flawed is, as I'll show you in a second, is because it cannot help itself. It always uses as a control a set of groups that have already been treated. It cannot help it, and you can't stop it. All right. And because it's doing that, if there is any heterogeneity in the dynamics of the treatment effect over time for those early adopters, it gets baked into the estimator and creates bias. And you can't stop it from doing it without a lot of manipulation. And I'm going to show you that manipulation at the end. So what is the preview of the decomposition? Here's the basic idea of the decomposition. And I'm going to do the decomposition for you. I'm not going to go through the Frisch-Waugh theorem, but I'm just going to show you what you find. So basically, two-way fixed effects will estimate a parameter that is basically, interestingly enough, a weighted average over a simpler set of those 2x2s that I just sort of showed you. Inside that two-way fixed estimator, it actually breaks down into a set of familiar 2x2s. That's what's kind of interesting. But the problem is some of those 2x2s are going to use treatment units, both as controls and treatment units. And you can't, like I said, you can't stop two-way fixed effects from doing it unless you kind of limit and structure the data in a certain way. The other thing that's weird, I'm going to say it's weird because it's not even theoretically coherent why you would like this. Two-way fixed effects also assigns weights to those simple 2x2s. And those weights are based intuitively on the size of a group, but non-intuitively, it's also based on how long a group, what share of the panel that you chose, what share of time that particular group was treated. And as we're going to see, there's a lot of arbitrariness in the choices that you're making all the time that directly affect the variance of the treatment dummies for those groups. And there's no real answer as to why you would do one thing or another, because that's not even theoretically relevant to what you're trying to do. So two-way fixed effects basically needs two assumptions, not one. It needs that what's going to be called the variance weighted common trend, or what you normally call parallel trends. We need the variance weighted common trends to be 0. It's just that we actually now are going to have a bunch of them, not just one, but a whole bunch of different ones. And you also need there to be no dynamic treatment effects, which all of us, when we have run those event studies, we can see estimates of dynamic treatment effects over time. So you already have reasons to be very scared. But under those assumptions, if you have variance weighted common trends equaling 0, and no dynamic treatment effects, then two-way fixed effects is fine. It'll estimate, though, a very weird parameter that still can't avoid incorporating those weights that we said into the estimate. It'll estimate what's called the variance weighted average treatment on the treated, which is a weighted average of all possible average treatment effects. And even that isn't necessarily the policy parameter of interest, because that one really is being driven by the eccentricity of two-way fixed effects. All right, so let me just try to break this down for you to hopefully it makes a little sense. So let's say there's two groups. This is going to be the notation we're going to use. We're going to have two groups. We're going to have a K group and an L group. K group is going to be an early treated group. They're treated early in the panel that you picked. And L is going to be a, quote, late treated group. And there's going to be one group that never gets treated, at least over the course of the panel. And we're going to say that's a U group. K and L, like I said, are going to describe the differences in time. These aren't just panel units, though. These aren't just cities. This is a set of cities that get treated at the same time. That's what's a group. Group is not a panel unit. It's a group of panel units that got the treatment in that particular year. All right? So it doesn't have to be two cities. It could be 50 cities. It's just that you have a set of cities that are treated early at the same time and a set of cities that are treated late. You're also going to have this variable here that is D bar. And what it is it's a fraction. It's the share of time that a group spends in the treatment status over your panel. Now, this is going to be the notation we're going to use. Delta hat. In my book, I always use delta for a causal parameter. So this is going to be the delta hat. It's going to refer to a 2x2. And it's the canonical 2x2s that we talked about. It's just going to be, it's a 2x2 for group A, and it's going to be a 2x2 for group B. And then it's going to have, some comparison. So how many 2x2s are there, right? Because we were looking at one earlier. How many are there? There's actually more than you think. So when there's three groups, there are actually 4 2x2s. And if you have four groups, it actually grows to 9. It kind of grows at a rapid pace. So in any kind of situation that you're working with, which might be 20, 25 groups that are being treated, you have an explosively large number of simplified 2x2s that are actually being added up into that two-way fixed effects estimate. All right, so let's look at it. There's actually K squared distinct 2x2s where K is referring to however many treatment cities you are, or treatment groups, and one holdout group that's not treated. So let's look at 3 groups, call them A, B, and C, and we have one untreated group, okay? How do I get to 9? Well, look, I have an A to B group, I have an A to C group, and I have an A to U group. But see, these A to B and B to A are not the same thing, because A is being compared before and after, and then B is being carried before and after with reference to the A group. So you have to do it again separately for the B group. When the B group is finally treated, it's at a different point in time. And as the control group, you're going to have to do the same difference for that timing. So you get a B to A, B to C, B to U. You get a C to A, C to B, C to U. And since U is never treated, it doesn't have a U to A and a U to B. So we're going to look at this. So that's how you get to those, that K squared with one holdout group. So let's return to our simpler example. K group treated at TK, L group treated at TL, and our untreated group. And let's just look at it in a simple scenario with trends. All right, so here we have group K. Group K is getting treated at T star K, pops up, after which it stays the same. L does not change at TK. It changes at TL, pops up, goes down. Group U never changes. We're going to call this period group pre. We're going to call it the pre-period. In between, we're going to call the mid-period. And after L, T star L, we're going to call it the post-period. There are actually 4 interesting 2x2s. For instance, there is an early group compared to a untreated group. And look how it goes. It goes post-K, pre-K. So it's going to be the mean right there. It's going to be the mean right there. It's it's going to be the mean for group U. It's going to be the mean for group K, right? That difference in differences is just corresponding to one of the interesting 2x2s. And then there's another one, LU. Group L in its post-period, group L in its pre-period, same calculation for group U. But now we get these K to L where we're comparing treated groups to treated groups just over windows of time. All right, so in the K to L group, look what we get. We only get the mid-period for this one. That's what OLS is doing. It's kind of working through all of these kind of simpler scenarios, all right? And it's going to actually, in this, leave out the post-period. So it's going to do a mean here minus a mean here, and a mean here for L as a control group, mean in the pre-period. But look, L's not treated. So in the worldview of diff and diff, that one, as I'm going to show, is actually a fair, safe 2x2 simple treatment versus control, because the control group is not yet treated and you're not using that period of time where it's not yet treated in the calculation. But look at this one. Let's look at the L to K. L to K actually is problematic because in the L to K diff and diff, you use here the mean of L minus the mean of K. And as your control, you have the group K minus the pre-period group K. But the problem is this time path has built into it a treatment. So you are comparing a treatment group to an already treatment group. And that two-way fixed effects cannot be talked out of doing it. All right? You can't make it not do it, not without a lot of manipulation. And that lot of manipulation actually leads us into the estimator that we're going to talk about. So the Bacon decomposition, named after Goodman-Bacon, the Bacon decomposition yields a weighted combination of each group's respective 2x2. So we're going to have here, notice there's the KU. I'm just combining this one and this one, right? So it's a summation, all right, with this weight, all right? And these weights are going to sum to 1. So we're going to get basically this 2x2 added to that 2x2 corresponding to particular weights. And then we're also going to get this interior K to L, L to K. So that's going to be this one plus this one. But the modifications of those two go through a series of separate weights, both these outer weights and these inner weights. So we need to break those weights open, all right? So what are these weights? So these weights, these SKU and SLU, they are basically a combination, a multiplicative of two types of things with a divided by this scalar, all right? So the scalar doesn't really matter, so we're just gonna, kind of look at this right here. What is this SKU and this SLU? It is based on, this is the 2018 notation. The 2019 kind of does it in a, what Andrew Goodman-Bacon said is a simpler, more intuitive way. I actually had already learned it this way, and so I don't really want to relearn it. So here we have the idea of the weight. You've got, if you have a large number of units that are treated, okay, and a large number of untreated units, it's going to be basically the product of the two. So if you have more treated units, they're going to be more influential in that 2x2, which kind of, I think, makes sense. Even if, if somebody put a gun to your head and said, tell me, do you think if you have more cities more cities in a group, do you think that's going to be more influential in your OLS estimate? And you'd probably said, yeah. I mean, under duress, you would have said that. And then you've got here this inner term, though. That's the part that's weird. You've got this variance term. This is a variance term. You've got this d bar times 1 minus d bar. Okay, and that one, if you were asked to guess under duress, you probably wouldn't know what to think because it's not particularly intuitive from a theoretical perspective. These SKLs, okay, here or SKL and the, right here on the outside, they describe those treated to treated situations. And what they've got is the same thing, however many of those scenarios that you have, groups, How many groups, do you have that are in group K and group L that's early related? And then they're multiplied by another variance term. Look at this variance term though, right? It actually is the same form. It's some term times 1 minus that term, which is what we have here. It's just that the term is now the difference between the share of those K and L units, okay? And then the last one is this mu KL, and it doesn't really have as easier of an expression, which is even more annoying about two-way fixed effects, okay? So 2 things come out of those weights. We said both of them. Group variation actually is playing a bigger role in that estimate with two-way fixed effects than city level variation. So if a group is two states that get treated in 1995, that's the 1995 group, and that variation is actually what's being used by OLS to calculate that parameter, not the units within. All right. So within group treatment variance matters a lot. Now, let's think about this, D bar times 1 minus D bar, right? Because this right here is also a weight. So whatever that term is, it's going to be blowing up the influential part of that specific 2 by 2 in that final OLS estimate. And what is it? Well, look at this. Let's say that a unit gets treated at the very end of the panel that you pulled. All right, 1990 to 2000, and it's treated in 1999. So it's only treated 1 year out of 10. So it's got a D bar of 0.1. Well, D bar 0.1 times 1 minus D bar 0.1 is 0.1 times 0.9. So that weight's going to be 0.09. Let's say it was treated in 1996, though. Then it's going to have a treatment share of 0.4. 0.4 times 0.6 is 0.24, and a D bar of 0.5. It was treated in 1995. Well, that's going to be 0.5 times 0.5. And everything else after that, that product, that variance is going to start falling. So it's like a parabola here is a function of D bar that actually peaks at 0.5. What does that mean? That means this weight here, okay, on that 2 by 2 is maximized by the groups at the middle of the panel that you pulled, and you may not have even had a good reason for why you pulled the panel the way you did, and it doesn't matter. Two-way fixed effects is nevertheless going to assign to your final estimate a weight that really emphasizes those groups at the middle of the panel. All right? Does the same thing with the dk minus d bar. Look at this, dk minus d bar, only now it's going to be situations where the difference between these groups equal 0.5. So it's still centralities. Let's say you have a group that's treated at 0.15 and 0.67. The difference between the two is a 0.52. That gives you a weight of 0.24. It's just not avoidable. Centralities in the panel are actually part of what is driving your estimate. So groups in the middle of the panel weight up their respective 2 by 2s. This is the first thing about two-way fixed effects that should make you a little nervous, as not all estimators do this, and it's not even theoretically clear why you should even care. Highlights the strange role panel length plays in OLS, because when you are starting your project, what do? You tell your RA or yourself, start it at 5 years before treatment. Or you say, start at 10 years before treatment. Or you say 5 years after treatment. Or you say 7 years after treatment. And why did you pick those numbers? Well, why not? You didn't think it mattered. So different choices about panel length, which maybe we didn't even give a lot of thought to, they're going to change not only the 2 by 2 value, but they're also going to change the weights that modify that 2 by 2. So if we move from 2 by 2s to causal effects, then we can, using the potential outcomes notation, we can actually break down each of those 2 by 2s, which are calculated with data. We can actually see what they map onto in terms of causal parameters as well as the bias. And that's the value of working with potential outcomes notation. It makes it very explicit what the parameter is, and it makes very explicit the biases that you need to somehow get down to zero through some sort of research design. okay? So you have the K to U, all right? The K to U, which was this scenario. And that K to U is going to be unbiased so long as you have a parallel trends assumption that holds. And the K to L, what's the K to L? It's this one, right? Comparing K, the early adopter, to the late adopter over the period of time where the late adopter has not yet been treated. Well, that also has a familiar parallel trends bias, and you just need that one to go to 0. But look already what's going on. Already what is going on is I have two parallel trends assumptions, and both of them are going to have to equal 0, not just one vaguely defined parallel trends assumption. It's a lot more specific. But here's the third one, the L to K scenario. All right. L to K was comparing a late treated group in its post period to its pre-period to an already treated group in the same set of periods. Now look what that 2 by 2 needs in order to be unbiased. Now it's going to estimate an average treatment on the treated for that post period, which means it's going to be estimating a period for this period. That's going to be the average treatment effect on the treatment unit. It's only going to apply to that late treated period. But in order for it to be unbiased, you need a parallel trends assumption, and you need that for the early group, the K group, you need a constant treatment effect, which we built into this example here. We built in constant treatment effects. Look, it just kind of levels up, But isn't it more common that you think that there's dynamics? Sorry, where did I go? Isn't it more common that you think that there's dynamics? Otherwise, why would you be estimating those event studies? So you usually think that, you know, an effect gets bigger over time, right? Or you think it gets smaller over time. So the first part, that's the parameter, you know, it's one of the parameters that we care about. The second part is that familiar parallel trends bias, only now we've got 3 parallel trends to worry about. The last one is a heterogeneity treatment effects bias. It's not a cross-sectional heterogeneity treatment effects. It's a dynamic heterogeneity over time. Because look, it's got to be that, you know, the effect in the post period and the effect in the mid period are the same in order for this to zero out. Adding all these together is how you get the decomposition, right? Here's the 2 by 2s. Now what we're going to do is we're going to substitute in KU, its causal representation for here, KL for here, LK for here. And you can see that is going to be a very, very, very long equation on the right-hand side, and look at all the sources of bias. Now, if we simplify that, you know, we kind of group them just notationally, we say that this 2 by 2, you know, that not 2 by 2, this OLS estimated parameter of interest with differential timing converges in large samples to the treatment effect that you care about, so long as you have that equaling 0 and that equaling 0. Now look at what's going on here though. You've got the variance weighted average treatment effect on the treatment group. So even in the best case scenario where that does zero out, look what you're getting. You're still only getting a variance weighted ATT. And we already said that variance that you're using in the weighting itself, it doesn't have it's not a theoretically interesting, relevant weight. And it's not necessarily the policy. This isn't necessarily mapping onto a policy parameter, okay? But maybe you can live with that, right? Maybe especially if all the cross-sectional average treatment effects are the same, then it doesn't matter how you weight them, you get that. But you can sort of see how many caveats that we are starting to make, okay? Let's look at these parts really carefully. Let's look at the variance weighted average treatment. All right, I did that one, right? So this variance weighted average treatment effect, it's basically ATT in the post period, that should be the pre-period. It should be ATT in the pre-period, ATT in the mid-period, ATT in the post-period. All combined, weighted. If they're different, That's where the variance weighting is kind of doing something weird. And if they're not different, it's fine. The variance weighted ATT, basically in that situation where all of the cross-sectional ATTs are the same, then the weighting doesn't matter, all right? Otherwise it does. Let's look at the variance weighted common trends or variance weighted parallel trends. Look how many parallel trends we've got, right? We need for that one to be 0, that one to be 0, and that one to be 0, right? Or these weights have got to apply in such a way that the sum of all three equals 0. Now that was with 2 treatment groups, but more than likely, especially if you're using, regional data, country level data, in the United States, it would be state level data or city level data, you're going to have way more than 2 treatment groups. Okay. I have a project that has 40 treatment groups. Well, that's going to blow up. The number of parallel trends biases in there is enormous. Now I got to make an appeal to each one of them. At some point, it starts to stretch the credibility. And then we have the heterogeneity bias. All right. And that's that dynamic. So I'm going to show I've got 25 minutes. So that's the problem with two-way fixed effects, is just the sheer number of biases being introduced, partly driven by that late to early treatment use and partly driven by just the sheer number of parallel trends. But, we probably always thought we were doing some sort of, specific case-by-case basis of parallel trends. Probably did think that, even if we had trouble I always had trouble articulating it. I had, in my mind, I had trouble kind of understanding it. I was always sort of like not really sure. It was funny, like I'm not smart like these guys, so I actually didn't know like what the problem was. But I had been over the last several years really uncomfortable with two-way fixed effects because I really wasn't sure how these untreated units were really being used, and definitely did not know about the late to early 2x2s. So there's these new papers that are coming out that are focused on the issues that we have with two-way fixed effects. And I'm going to discuss one because it's unbiased and consistent. It's by Callaway and Sant'Anna. It's Brant Callaway at the University of Georgia, Pedro Santana at Vanderbilt University. It's R&R at the Journal of Econometrics. And due to time constraints, I'm only going to cover that one. And I'll tell you some more that you can look at the end. But I'm just going to call it CS. And if we have time, I'm going to go through a simulation. I really hope we have time. So when are you going to use this estimator? What are the situations? More than likely, it is every situation that you have ever thought of. It's going to be situations where treatment effects are heterogeneous cross-sectionally. It's going to be situations where treatment effects change over time. It's going to be situations where you believe the short-run effects are more pronounced than the long-run effects. It's going to be situations where you think that people treated in a recession have different treatment effects than those in an expansion, right? It's all these situations that you were kind of like in the back of your mind thinking about, and they may even have been the questions that you were interested in, all right? So here's the preliminary situations that you can use it. And the paper is a typical econometrics paper in that it's concerned with identification, estimation, and inference for calculating average treatment effects. So the situations are multiple time periods, not just 2x2s, multiple time periods. Variation in treatment timing. That's the differential timing that we actually probably were hoping we were in. And then all you need is parallel trends, even parallel trends with or without observables, but not that weird parallel trends that variance weighted parallel trends, right? And you don't need the heterogeneity, constant treatment effects. So here's the parameter that you are interested in that Callaway and Sant'Anna framework. It's called the group time average treatment effect on the treatment unit. It's called group because it is going to be a specific average treatment effect for a set of groups. All right, so that could be the early group, that could be the group treated in 92, 95. So it's going to be a unique average treatment effect, but it is going to be the dynamic treatment effects because you're going to calculate that group average treatment on the treated at particular points in time. All right. So it's kind of like, let's just say it's like that event study. The event study is totally different, but let's imagine it's like a group specific event study. okay, in relative time. So the group time, average treatment on the treated, is for a specific group at a specific point in time. Groups are basically cohorts. Method's going to calculate a cohort-specific effect per period, which is going to give you a lot of treatment effects. And if you run this in R, you're left with a bunch. Now, it doesn't matter how you do the calculation. It actually does work with OLS. So those of you that really want to continue to use regression, it'll do it. It'll do first difference. It'll do non-parametric methods. So it's very general, and it can still use regression. It doesn't directly restrict the heterogeneity at all, whether in regards to the timing, the evolution, or the covariates, or cross-sectioning. Okay, so you don't even have to worry about heterogeneity at all with the group time average treatment on effect on the treated, because look, the heterogeneity is going to be one. It's like you're getting a group-specific average treatment effect. So it's like the heterogeneity is a part of what you're doing. It's all just going to be how you're combining them. They're going to provide a way to aggregate over all those many parameters into a single average treatment effect, or maybe groups of average treatment effects, like in relative time, depending on what you want. You can also do event studies with it, and you're going to use bootstrapping for your inference. Notation here, we're going to have T periods. Groups are either going to be treated or not treated. A group, like I said, is going to be a dummy variable signifying a group. Equals 1 if an individual set of units are treated at that time period. All right, so it's not a dummy for a panel unit, it's a dummy for a group. C is binary, and it indicates a control group, a holdout group, all right, a group that's never treated. Now, depending on when you pull the sample, you may mechanically have a group of units that are never treated, but if you want to stretch the panel out even longer, such that there's staggered adoption, well, it's just going to use as a control group a not yet treated. And what that means is that there's a limit to how many treatment effects you can actually calculate. You'll never be able, under this estimator, to get a group time average treatment effect for that last group, because it will never use as a control a already treated group. And at the very end, there are no more. There are no more never treated groups. It's going to have a propensity score based on covariates that are going to function as weights. So for assumptions, panel data can also work with repeated cross sections. Conditional parallel trends, there you go. All right, is a set of, it is group specific parallel trends with respect to the untreated, or the never treated, or the not yet treated. You cannot look at the switching of treatment going from 0 to 1 and 1 to 0. And then you have a common support assumption, which is basically the very common situations with propensity scores. Here is the estimator. All right, here's the estimator. And it's going to use in the estimator what's called the long difference. All right, so this is going to be the long difference. It's just a before and after calculation for the group and the untreated group. All right, so it's a 2 by 2 for the treated group and the untreated group. It's just that it can go at any point in time, right? It's denoted G because G indicates a period of time. So you're going to kind of go like, the just prior to treatment. All right, just prior to treatment, what's going to be used for your parallel trends. That's what you need for your parallel trends. And it can go out as far as you want to. All right, so that's why it's a long difference. It can even be like, 50 years later for all you want. It can be 1 year, 5 years, 10 years. And here are the weights. All right, the weights. I don't have a lot of time, but I'm going to distribute these slides as well as a do file, and you can study these weights very closely. But look, here's a dummy, and here's a mean. Here is an odds ratio, and here's a mean of that odds ratio based on the propensity score associated with the not yet treated. And basically this weighting by the propensity score is basically going to kind of recalibrate those long differences such that you are kind of comparing groups to not yet groups that are pretty similar to each other, right? So it's kind of got baked into it, some of that matching methodology that, we sort of find appealing in a lot of the work that we do. Okay, I'm gonna skip that. So the method proposes just going to be identifying very narrow average treatment effects. You can aggregate. They're going to present 2 methods for aggregating. It's going to allow you to estimate pre-treatment coefficients in an event study in the pre-treatment period. And the reason that's valuable is that Sun and Abraham show that even those pre-treatment coefficients are messed up. Those pre-treatment coefficients, according to Sun and Abraham, actually are contaminated by the treatment effects. Two-way fixed effects is doing so many things wrong, okay? And then the inference is going to come from a bootstrap. So let's do this. I've got 15 minutes, all right? I've got 15 minutes. What I want to do in these 15 minutes is, got this here, right? So I'm going to go through a simulation. Apologize, I have cuss words here, but we're going to do a simulation. This is a simulation that I got from my good friend Andrew Baker at Stanford University. He's on Twitter and is always talking trash about economics, but talking trash is a Southern United States slang. So he's always being mean to economists. But this is the simulation. What we're going to do in this simulation is we're going to create 40 states, all right, here, right? And inside each state are going to be 25 firms, right? And firms are going to be designated with a firm fixed effects. It doesn't really matter. It doesn't really play a big role, but basically the firm fixed effects is going to be a random draw from the uniform distribution going from 0 to 5. And you can just think about it as the unobserved heterogeneity that doesn't change over time, okay? Then we're going to have 30 years, all right? We're going to have 30 years. Let's see what we get. 30 times 25 times 40, 30,000 unit, 30,000 rows, okay, for 40 states and 1,000 firms. And what we're going to do now is we're going to build our groups, all right? We're going to build our groups. I say the treatment effect is going to be 5 on average. I can't remember if that's true. I think it's actually 7, but I don't know why I did that. But anyway, we're going to have here 250 firms. We're going to have group 0 to 4. Actually, it's going to go from 1 to 4. There's going to be a set of states that are treated in the first 20, first quarter of the sample, set a group in that, quarter to 50th, the median to the 75th, and then above, okay? We're going to call them group 1 to 4. And we're going to indicate a treatment dummy. All right, let's just look at this. Here, all right, 4 groups, 7,500 per group, 7,500 firms. Treatment dummy, we got, 15,000 units a time, firm units a time, where they are treated, and 15,000 when they're untreated. They're just getting treated like we said in 1986, 92, 98, and 04 for a panel that goes from 1980 to 2009. So it's actually a couple of things about this. Notice this is a fairly long panel, right? That's going to matter. It's a fairly long panel. And what's not going to matter is the firm variation. It's going to be the group variation. We're going to have 4 groups. Now I'm going to build in a data generating process, standard normal. And this data generating process, okay, we're going to have an error term with mean is 0. And then we're going to have a treatment effect for group 1, right? Treatment effect for group 1 that has a mean of 10, all right? For group 2, mean of 8. Group 3, mean of 6. Group 4, a mean of 4. All right, so basically this is that situation we were saying. Maybe the early adopters are the ones that have the biggest treatment effects, like, in kind of like a modified Roy model, it's like the ones that are sorting into treatment, in the early treatment periods. Well, maybe they sorted into treatment because they had the most to gain, okay? And then it got incrementally lower. This is that cross-sectional treatment effect that we were talking about. Okay. All right. So I'm going to do 2 things here. I'm going to generate a variable, an outcome variable called y, and I'm going to generate an outcome variable called y2. All right. What is y? Y is going to be the outcome based on firm fixed effects and time fixed effects, as well as dynamic treatment effects. How did I get the dynamic treatment effects? Hold on. Yeah. How did I get the dynamic treatment effects? Notice how I did it. In a given year, I have some treatment effect, and the treatment effect is going to get bigger over time because it's basically going to be in the period immediately after. For instance, for group 1, it'll be a 10. In 2 years, it'll be a 20. In 3 years, it'll be a 30. But for group 2, it'll be 8, 16, 24, and so on. For group 3, it'll be 6, 12, 18, and so on. And for group 4, it'll be 4, 8, 12, 16. See how it's getting bigger in those group time since it's growing over time? Well, remember, with two-way fixed effects, that would be that bias term, right? That's going to be that bias term. And the way that we're generating the data, we're guaranteeing that common trends holds, but we're not for y guaranteeing that that holds. In fact, we're mechanically making it not hold. All right, so I did both of them. But for here, for y2, there is no such dynamics. It's just going to be the mean for that group, which we said is 10, 8, 6, 4, times whether it's treated. All right. I also have some leads and lags that I can put in. All right, so let's look. All right, let's look. We've got here, we're going to look at the effect of the treatment on y2. And remember what I got here, TI, 10 plus 8 plus 6 plus 4 divided by 4, it should be a 7. The mean average treatment effect on the treatment group should be 7, and it's a 7. And that is the scenario that we were always sort of learning in our panel classes with fixed effects. It is consistent. Okay, it is consistent under constant treatment effects, not constant cross-sectionally, right? Because we built into it heterogeneity across groups. It was treatment effects over time. All right, now what happens if we have heterogeneous effects over time when we use two-way fixed effects? Look at that. It flipped sign. It was not only biased downward, that would be like a pure form of attenuation bias that you might get with measurement error. No, that's not what's going on. It's like linear, right? Go back to this. It's linear. The bias enters in linearly, not just like asymptotically towards 0. So if it's big enough, it can cross the 0 line. Is screen share turned off?
It's working fine for me.
Okay, hold on. Let me go back to it. Hopefully that fixed it.
Yeah,
so, okay, so even the event study is flawed. Even the event study is flawed. Okay, let's look at this, right? You thought that this is the event study here. This is going to be the leads and the lags. You would hope that the leads would be 0 since we mechanically built them to be 0. And it is not. None of them are 0. That's terrifying. Not only that, look at this. We've got treatment effects here that are negative, and that is impossible. Because look, that's always positive. Treatment effects are positive, dynamics are positive. So what are you going to do? Well, you can use Callaway and Sant'Anna. All right, Callaway and Sant'Anna is this. Let's calculate this non-parametrically. All right, we're using the just the code. Now this is going to only calculate a bunch of group time average treatment on the treated, but I just want to simulate something. Okay, so what do we need? We need dummies for G. That's what I'm going to do first. we need a propensity score. So that's what I'm going to do second. But this propensity score has to be limited to a treatment group, group 1, and a not yet treated group. That's the you cannot use as a comparison a already treated. So we're building into it. We're building into it the already not the never treated as a control. What else do we need? We need the long difference. So we're going to have to do all these independently. Okay, so we're going to do that here. And we need these means. Okay, we need these means. Then we're just going to build weights in. Weight 1, weight 2. There it is. Right? G1 over G1 mean. G1 over G1 mean. 1 minus G1. 1 minus. So you're getting the whole thing. Okay. Then we get each of our individuals for the 2x2s of the long difference here. Okay. And look. Now we know, let's go back up here. For the first group, okay, which is right here, group 1, here, group 1. The mean treatment effect is a 10. So Callaway and Sant'Anna better equal 10. Oops. Let's do another one. Just because we have time. Let's do the group time average treatment on the treated for the T+2 period, right? That one should be a 20. Oh, sorry, it's supposed to be a 30. I skipped it. I skipped one. Sorry, it's supposed to go right here. Well, that still holds for the T+3 period. It should be a 30, and it is a 30, right? So it'd be 10, 20, 30. So you get the idea, all right? You can even use regression to do this. I may have regressions in here. You can even use, you can even do the event study, all right? Now you don't want to do it using the status simulation I did because it's just too cumbersome. What you're probably going to want to do is use Brent Callaway's R package called DID, which can be installed from GitHub. And right now, we are in the process of creating the Stata ado package. All right, so eventually you will be able to do it. All right, so you're probably going to write a difference in differences paper. You're going to probably want to use two-way fixed effects for one reason and one reason only, because it's one line of code. It is easy to do. You think you understand it, and calculating the standard errors and including covariates is easy. Do not do it because it is biased of unknown amount. Goodman-Bacon shows the bias of two-way fixed effects. It suffers from a particular kind of linear attenuation bias, and it's even theoretically possible that it flips signs. CS is an excellent alternative because it doesn't suffer from any of those biases, and it is currently available as a canned package so that you're not having to go through and do all that manually. But there's other options. For instance, there's Athe and co-authors matrix completion for panel data, which is also available, I think, in R with, I think it's called gsynth, which is a very robust R package. There's a stacked method that Singas, I hope I pronounced that name right, either Singas or Sinders, probably not even, that's not right, et al. In their 2019 QJE, they do a stacked method where they basically turn a bunch of differential timing scenarios into a simple set of before and after, where they use as their control group just all the other control units, stack all those simple differential timing, and then just run a simple before and after. When you do that, you do not have when you do that, you can do all that OLS stuff, and it's not going to be biased because the simple 2x2 is never biased, even with heterogeneous treatment effects. And then there's also several excellent papers by a French team, de Chazem Martin and de Holfeld. But remember, what is the problem? Problem is heterogeneity, which creates a problem for two-way fixed effects, because two-way fixed effects uses as a control already treatment effects. That is immoral, not to be kind of joking, but you shouldn't do it because it's a form of deception, even deceiving yourself, because it is not unbiased. And that's the source of the two-way fixed effects bias. Okay, so exactly 60 minutes. I can stay around and answer any questions to the best of my ability. But for those of you that need to leave, I know you need to leave. So that was the bulk of that was the presentation. There will be more about this in the book that's coming out in January. You're welcome, Cunningham. Good to see you.
Thank you so much, Scott, and thank you for the simulation. I think that was very helpful and puts things into perspective as well.
I'll send the simulation to you, and then as well as the deck of slides.
Perfect, and we'll share it with everyone. So we can